here are the elements that we have in our model. We have observed items that are listed here. There are 50 of them. And we link these observed items to our latent factors through loadings. And we, as the researcher, would give these factors names and context. Each observed item has measurement error with a variance associated with it. And then the latent factors are allowed to covary if we want them to, which is typical that we do. These are all of the main elements of the model. So now we can take each element and then tack a name to it using our literal notation in order to keep our free parameters sort of grouped together and named appropriately. Overall, we can see we have 3 types of free parameters to worry about. We need to set priors for factor loadings, for the error variances, or the entire covariance matrix if we had these covary. And then we need a prior for this covariance matrix over here for the latent factors. This slide looks maybe a little messy at first, but it is just mapping our parameters to our priors. So first we can look at our loadings, and that's these lambdas right here. And we can map those on to a normal distribution. So we say lambda is distributed as or by, and n would be the normal distribution. The normal distribution is defined through a mean and a variance hyperparameter. This is how you know exactly what that distribution looks like. Second, any variances that we have in our model, which we have a bunch here, those would be modeled using an inverse gamma prior. The inverse gamma has 2 hyperparameters. One is the shape and the other is the scale. If alternatively, if we had an entire covariance matrix over here, then we could use the prior that we have set down here. So the covariance matrix, wherever they are in the model, whether it be this one or this covariance matrix over here, will always get an inverse Wishart prior in Mplus. This is a multivariate prior that maps onto a matrix. And so in this case, it's the covariance matrix. It has 2 hyperparameters. This is typically a positive definite matrix. And then new right here, this would represent the degrees of freedom for the distribution. In this case, each of these hyperparameters can be modified to change the degree of informativeness for the distribution. So now we have our priors and we can look at our input. So this is the beginning of our input. I just go through and talk about what the data file here is, but I already mentioned that we're working with the Big 5. It's a 50-item questionnaire where the items are said to break up into 5 different latent factors. We have a huge data set of 10,000 people, and let's go through and check it out. So we can set the variables up first. We call in the data file and then say what variables are in our data file and in what order. I'm going to narrow down and only use these 50 items to form our 5 factors, and I will let it know that these are categorical items. Next, we can set up the estimation information. So we use the Bayesian estimator here with a minimum of 500,000, this says 50, but it's actually 500,000 samples forming the chain, and a maximum of 1 million. So I deleted a 0 in my brain when I wrote this, but 500,000 would be the minimum number. If you play with this, make this smaller so it won't take as long to run. But this is how we would set up the number of samples that we want to be in our chain, both a minimum and a maximum. I also, just to show you, I occasionally do this, override the default setting of 0.05 for the potential scale reduction factor. I override it to be a stricter 0.01. You don't really need to do this. There's only a few times that I would actually recommend it, but I show you how to do it here just so you can see. Here is the model. This is how you would set the model up. The by statements show you that these are factor loadings, and we can see which items will form each of these latent factors. We actually name the latent factors whatever we want to. And so we say that these first items are going to form what I call factor 1. Next, we can request what kind of output we want. So we say, oh, I'd like Tech 1 or standardized results, then we would put that here. This next line is very important. We can save out data that we can later read into R. So the MCMC chain information gets saved out into almost a data file. And then R can read that in to make some nice plots for us. And then we can ask Mplus to make plots for us as well. So here's the output. Information is first given about the Bayesian estimator. We can see that a probit link function was used because I said that we had categorical items being used as the outcomes. And then the rest of this would just represent the other default settings that we specified, the maximum number of samples in a chain, and then we went through and overrode the convergence criterion, and that is listed here as well. Then we can get an initial look at the number of people who are selecting each of the item categories. So these items were on a 5-point scale, and we can see the proportion of people who selected each of those categories for each item. So some summary statistics would come next. Then we can see this command right here, this line that comes out. So this is good news. The model estimation terminated normally. But then it says, use the FB iterations option to increase the number of iterations by a factor of at least 2. I will go over this a lot later, but this is a really good recommendation to follow. You initially run the model and then want to make sure you've obtained convergence. And the best way to do that is to double check by basically doubling the length of your chain or more and checking to see that convergence indeed did still remain. So this is in the transparency lesson that we have later on. I'll go over that. Then we have some model fit information here. Look to see, does your posterior predictive p-value point toward model that fits or not? It doesn't. But you can look at that lesson to learn more about those fit measures. Then we get our model results. So the first set will be unstandardized factor loadings. For the Bayesian type of results that we're getting, the default estimate is going to be the median of the posterior, which is a really good default. Sometimes people will override this and use the mean or even the mode sometimes, but the median I think is a good default to stick with. Next in line, we have the posterior standard deviation. We have a p-value, which is computed, and some Bayesians will not like this. And then a 95% credible interval. We have a lower and upper bound given for that. And then an indication of significance, which again, some Bayesians won't like that, but Mplus maps it on there for people who are interested. The loadings will show you how related the items are to the latent factors. So higher loadings indicate a stronger relationship. And often people will look at the highest items that are loading on a single factor to help drive the substantive meaning and even the name of that latent factor. And the last point here is that we can see that the first item on each factor is fixed to 1.0 because that was the default setting. We did not have to write that in the code. It just naturally happened from Mplus. Next, we get information for the factor variances. And we may want to look at the correlations that come later if we asked for standardized results, because those might be more meaningful to us. But these would certainly be something you'd want to narrate in your findings to show how overlapped your factors are with one another, how they co-vary with each other. Then we get thresholds. These are used to compute the proportion of people answering each of those item categories. So I mentioned that the items had 5 response categories. So the way Mplus works is it creates a threshold or a cut point. If you have 5 categories, you need 4 thresholds per item to compute that. And so you would get in the output next, you would see these thresholds. It's basically just telling you how it's computing the number of people that fell within each of those item categories. Next, we see factor variances. And then we go to Tech 1. And so Tech 1 will let you know what parameter numbers Mplus has assigned, or what parameters have been assigned to each number. So it'sMplus's internal numbering system for the parameters. So each parameter that's free and being estimated gets a number associated with it. This becomes important if you have a convergence problem. Mplus sometimes will tell you, you know, parameter 42 didn't converge, and then you need to look at Tech 1 to see what parameter 42 is, and then troubleshoot why maybe it didn't converge. Maybe your chain needs to be longer, or the prior setting is strange. Something might be wrong in the model. So knowing the parameter will be helpful there. If you ask for standardized results, then those will come up. You will start to see all of the same things that pop up in the unstandardized, except you're going to see them in a standardized metric. I think actually that comes before the Tech 1, so these got flipped, but they're all sort of in the same spot in the output. And then you would see starting values. So if you have convergence problems with a parameter, it could also be useful to check on the starting values that were used to see if it's starting in a really wild place. You may need to help it start in a more reasonable place for factor loading. Maybe a starting value of 0 would be reasonable. But I always like to look at these just to see where everything is starting in the process. Then we can see a list of priors for all of the model parameters. And in our model that we have here, we have a lot of different priors, and I won't show you all of them. Here we just used default priors, and later I'll show you how to do user specified priors. But either way, the list of priors will always be down here at toward the bottom of the output. And we can see that the default settings, for example, for a normal prior on a categorical item, the default setting is a mean of 0 and a variance of 5. And that is listed in the Mplus user guide. If these were continuous items, you would see 0, and then they would write infinity. They don't really mean infinity, but they used a huge number, 10 to the power of 10. But for categorical item, the default prior is 0, 5. We can also see down toward the bottom of the list of priors that we have the default setting for the inverse Wishart. Actually, this is not the default setting. This is something that I overrode in part of the code that I didn't show you. But in this, we have an identity matrix, and then number of factors plus 1 is what I used here for the degrees of freedom. So you can go through and see what prior settings are default, or when you've gone through and changed them, they would all appear right here in the output. This next part of the output just tells you that you have access to various plots because you put that in the code. It will depend on whether you use a Mac or Windows on if you have access to plots. So I use a Mac, and I always end up calling the plotting information into R, and that's very helpful for me, but you may have a different system that works better for you. The information that is called out into R is saved in this file that we asked it to save. And this is the part of the output that tells you that the file was saved and what order of information appears in that file. So Mplus would read in this part of the output and that data file that it created. Actually, R would read that in and then be able to plot everything that we did earlier. So this part tells the ordering of the information in the file that was created. So now we can look at informative priors just to see how the code is set up. So here we would have our model, and what I've done is just made this really spelled out. So factor 1 by, and we've got our 10 items. We have labels next to it, E1 to E10, and then N1 to N10, so forth. So what I've done is I've given every single loading its own code or label. And then down here, this is my factor covariance matrix. I've had to spell each one out and give every single one its own loading or its own label. That way, if I want to place a new type of prior distribution on that covariance matrix, I'm able to with these codes. And so basically you restate your model, but in a way that has labels next to every single free parameter that you're estimating. Model priors can then be implemented. So we have here for our loadings, this is for our extroversion factor, we have new priors that are set up. Normal, but within different mean and a different variance hyperparameter. So maybe these came from previous research or expert opinions, something like that, but we have some informative subjective priors that we want to include. This is how we would do it. We would map it on to these labels that we created on this slide, and then use that label to help to define the prior and say it's distributed normally, but I'm going to override the hyperparameter settings here. Next, we can change them for our next factor, and then next, and next. So all 5 factors can end up receiving informative priors if you choose that. Now for the inverse Wishart prior, there are different types of settings that you can do, and you would go through and be very careful when you modify this prior. But what I've done here is I've created an identity matrix, and then this P+1, so P is number of dimensions, which is 5 because I have 5 factors, so I use 6 here. This is just another common diffuse prior setting that can be implemented, so it's different than the default setting that Mplus uses. And I just show you because I want to, I guess, warn you that when you have an entire matrix, it's not like just specifying a prior on that matrix. And Mplus, it's a little bit counterintuitive because it has you break the elements apart within the matrix and then take a univariate element and then place a multivariate prior on it. It looks a little strange in Mplus. Other programs don't look like this, but it does take this information and combine it all again and form the matrix and then form the multivariate prior. It's just how you specify it is element by element. And so all of this stuff just represents one matrix, even though it's 15 different parameters.